Okay, today's lesson is about model testing and evaluation. In the past lessons, we have learned what are machine learning models, and we knew, right? So when we have a data set, we divide it into two, like the training set and the testing set. And then first we uh, get the training set and using a defined well-known machine learning algorithm, we learn with the data set, training set, right? And then we get a model, right? That model will be used for testing to see how accurate that means, whether that particular trained model can be used for data that were not used for testing, right? So we are using the testing set for uh, testing the model, where we are using the test data and see what will be the predicted outcomes from the model, so that we can get an idea. We can statistically get the value where the model is, how much the model is working well for the unseen data. Right? Unseen data means the data that uh, haven't seen during the training process. Right? So in this lesson also, we are going to discuss about how the models are tested and evaluated. Before that, let's see a very common problem that we will meet in day-to-day machine learning tasks, which is about unbalanced data classes. Right? This happens when we have several classes of data in the classification scenarios, right? Where some of the classes have less amount of data than the other classes. So just let me explain with some example. Right? For example, suppose you are going to you are going to train a binary classifier for uh, patients with HIV positive and patients without HIV infection, right? So suppose with some X variables with related to blood samples or something, they are going to predict whether that particular patient has HIV. Right? In that case, your data set would be high, most probably be not balanced, right? Uh, what does it mean? So when it comes to the proportions of the uh, patients that are having HIV positive would be very low, for example, like less than 1% compared to the patients that are not infected with HIV. Right? That is the nature, right? So when you get the data set from an hospital with the patients that have applied for uh, blood tests or the test for HIV infection, most of the patients would not be having HIV, right? So in most of the cases, with related to diseases, this thing would happen. That means the data set would be highly unbalanced. What is the balanced data set? So in that case, we expect that the proportion of each of the class should be equal. Right? If it is a binary classification problem, there should be 50% of data from uh, HIV positive cases and 50% of uh, cases from negative cases. That means without HIV positive, right? HIV negative. 50% for HIV positive, 50% for HIV negative, right? But that is not the case, because in the nature we find very highly unbalanced data sets. In these scenarios, when you try to train a machine learning model, this should be highly inaccurate. Right? Highly inaccurate in the sense you will get, so we will see in the definitions of these evaluation matrices. So in that case, you will find that although you will get a very high accuracy, the model is not giving you what you want, right? So that means, for example, the model may train to give uh, all the for all the data points, the model will try to give as not infected, right? So when that is the case, the model would be 99% accurate, right? Did you get the point? Right? Suppose a binary classifier which has learned to give 100% non-infected outputs as the Y predictions. That kind of model would be giving 99% accuracy for a very highly unbiased data set, which has 1% infection rate and 99% non-infected patients, right? Because when you give when you give as non-infected for all the scenarios, for all the data points, that means then what happens is that the accuracy would be like 99%, because the failing 1% is only for the patients that are really infected, right? So, but that is not we want, right? Because what we want is to identify the people uh, who are infected, right? If they are infected, we should be able to identify them, right? Not like we can avoid them getting detected, right? So in this case, this data balancing is very important, right? That is why we need to avoid imbalanced data and make the imbalanced data balance as much as possible for building a correct classifier, right? Much accurate classifier. So when you get so what really happens when you have highly unbalanced data is that majority class, say in this example, the class which has a higher number of data points where the patients are not infected will get a higher priority, because there are most of the data points belongs to that particular class. This class would be dominated during the training process. So during the training process, the minority classes which have lesser number of data points will almost get neglected, right? So the model will try to learn, right, this majority class. So the model would try to optimize only for the majority class and give higher accuracy for majority class, but will totally forget the minority class, right? So that is why the model would not be able to classify correctly for the patients who are really infected, right? So in order to handle this imbalanced data, there are several techniques, right? That is, we can do some apply some techniques for the data set, and there are some other techniques during the training process also. So when it comes to balancing the data set, there are mainly two techniques. One is known as the undersampling, where you remove some random data points from the uh, majority class, right? Till the class, the data points in these two classes are two or many classes are equal, right? That means you can suppose that is a binary classification problem. You can reduce the majority class uh, up to the data point size of the minority class. So that is what the problem is, that when you reduce the minority class, when you reduce the majority class, you get very lesser number of data points, right? In that case, you would lose most of the information that you have in your data set. When it comes to oversampling, so the second technique is known as oversampling, where you don't remove any data point from the majority class or anywhere. So what you do is you duplicate the data points in the minority class so that the class sizes are equal, right? So the idea of balancing is that you want to make sure the classes, the Y classes, the Y label classes are equal in the data set, right? So with the undersample, what you do is you reduce the high high frequency majority class. With oversampling, what you do is we duplicate the minority class with replacement. So we have learned about the with replacement technique in the bootstrap example, right? That is what we are going to do. So with oversampling, we are not really duplicating exactly the same data set. So what we are doing is we are taking the duplicates with replacement. That means some of the data points may get duplicated during the process, right? Like we have learned about the bootstrapping technique, right? The problem with the undersampling is that you will get lesser number of information because you are removing much of the information from some of the information from the majority class, right? So the problem with oversampling is that because you are duplicating the minority class, there are actually there would be only few number of data points, right? So although you are duplicating to balance the count, still you would be having the same a few number of data points in the minority class. So in that case, uh, because there are only few data points that are duplicated, the model will try to overfit for those data points because they have a very high number of duplicated data points. So that would be so when you have overfitting, what happens is we have a high variance problem, right, for the minority class. Right? That would not happen to the majority class, but when you are oversampling, the an overfitting issue can happen for the minority class. So in order to reduce that effect, you can actually use some data uh, creation technique, like you can synthesize some data for the minority class, which may not be as which may not be close to the real data that you would get, but there are some statistical techniques where you can make some assumptions of the distribution of the minority data class, and then you can uh, create some more data so that you can oversample the uh, minority class without duplication, right? So one of the techniques is known as the synthetic minority oversampling technique, or SMOT, to create synthetic data. And there are some other techniques as well, but and but sometimes those techniques may work, sometimes they may not work. So that is, however, one of the techniques that you can use, right? So those are the techniques that you can use for to manipulate the data set before we do the training process to make sure the data is balanced, right? So when you are training the same samples, training with the machine learning, uh, there's another technique known as cost-sensitive learning technique, where you can give a higher weight to the minority class during the training process, which is not given for the majority class, right? For example, suppose minority class is 1/10 of the majority class. So when you are training with the minority data points, you can give a higher weight so that the machine learning model would be highly affected. That means 10 times much more affected with the minority class when you are training with the minority data points, right? So that would still be having some issues, like maybe some things like overfitting, because you are simply giving higher weight for these data points. So that is also another, however, one of the techniques that can be used. So that is a technique where we are not applying on the data set, but during the training process, we can identify the minority classes and then we can give higher weights, or identify the majority class and give lower weights compared to the minority class, so that we can balance the effect of the machine learning model depending on the class proportions. Right? In the real world, what happens is we are using a combination of all the above techniques. Right? For example, if there's a very highly unbalanced data set, what you can do is you can undersample to some extent in the majority class, then you can oversample for some extent in the minority class, then you can use cost sensitive learning for for some proportion to magnify the minority class, and still there would be some data imbalance in the classes, but that would not be a major problem, right? So that is how we do the data balancing in the real world, right? However, so when you are using the ensemble techniques like bagging and boosting, uh, inside these techniques, the data balancing technique is automatically applied, so you may not have to worry about these things. For example, in the random forest, we have learned that it is using the bagging technique, and with bagging technique, because we are using bootstrapping technique, we are uh, taking the copies of the original dataset with replacement to make several data samples for different models. We can achieve some form of data balancing, right? So that is one of the advantage of ensemble methods as well, right? So that is all about mm, data balancing that we have to know, right? And now let's talk about the hyperparameter tuning, right? So if you know, or if you have heard about hyperparameters, so this is a set of parameters that the user, or the data scientist or the data analyst have to manually configure, right? So the parameters are the variables that would get changed during the machine learning process. For example, beta 0, beta 1, beta 2, beta n, right? So those are parameters which we are going to learn during the learning process. But hyperparameters are not the parameters, but a set of configuration variables where the machine learning data scientist or the analyst have to initialize or set at the beginning of the process. For example, the learning rate, which we generally take as 0.01, or the maximum tree depth in decision trees or uh, random forest kind of algorithms, right? And the regularization constants that are used in different machine learning algorithms. Those are some of the examples for hyperparameters, right? So the users can set some of the values with their past experience, but that may not be exactly uh, be the most suitable or the optimum hyperparameters uh, that has to be used. But in order to find the optimum hyperparameters for the machine learning process is known as hyperparameter tuning, right? So the idea of using the hyperparameter tuning is to get the better machine learning process, and so that we will get models with the lowest level of errors, right? So in order to get the best values for hyperparameters, we have to train several machine learning models with trial and error, so which is a time consuming process. So there are some techniques that are uh, developed for automatic hyperparameter tuning without manually having to train the same model again and again for, for finding the optimum hyperparameter values, right? So one of the hyperparameter tuning is known as the grid search, right? So in this technique, what we do is we are taking the hyperparameters and we make a grid out of it. For example, we can have we can map the two hyperparameters together and make a grid like this, right? Where the hyperparameter with value this one and the hyperparameter 2 value with this one, and hyperparameter 1 with this value and the hyperparameter 2 value with this one, and so on. We can have several grid points in the hyperparameter space so that you can train models for each of these hyperparameter points, and you can find which of the hyperparameter combination, that means either sometimes this hyperparameter 2 with value this one and the hyperparameter 1 with value this one would be the best one, right? For example, hyperparameter 1 is the learning rate, hyperparameter 2 is the regularization constant, right? So hyperparameter 1 with learning rate 0.05 with regularization value some amount, right? So this would may be the optimum value. So you can, by looking at testing, making machine learning models for all of these points, you can find the best values, and then you can search around these the best optimum hyperparameter value. So that is a technique where you can use for finding the optimum hyperparameter values, right? So that is known as the hyperparameter, which is known as the hyperparameter tuning, right? So when you are evaluating, when you have lesser amount of data points, you can use cross validation for calculating the error. So we are taking the hyperparameter values that are giving least amount of errors, right? But the problem with this approach is that when you are having many number of hyperparameters, this grid technique would not be scaling, right? For example, suppose now in this case we have two hyperparameters. Say here we are using 10 values for hyperparameter 1 and 10 values for hyperparameter 2. So there would be 100 machine learning models you have to train, right? Suppose there's another hyperparameter known as maybe like maximum tree depth or something, which is hyperparameter 3. That then suppose that would also have 10 values. So then there would be 1000 10 to 10 to 10 1000 data points, where 1000 hyperparameter points where you have to test with trial and error, right? So this should be very expensive, right? Because training 1000 machine learning models with 1000 different values for hyperparameters is very expensive, right? So when you are having 3, 4, 5, 6 number of hyperparameters, that would not be possible. That would not be practical to test for all the grid data points when you are having higher number of hyperparameters, right? So one of the better technique that can replace the grid technique is known as the random search, right? In this technique, we don't have a grid like we do in the grid search, where each of the point values are systematically selected. For example, hyperparameter 2 values are systematically selected with equal distances. Hyperparameter 1 values are selected with equal distance and so on. But in the random search, we select some random value with hyperparameter 1 and hyperparameter 2. Hyperparameter 1 and hyperparameter 2. Hyperparameter 1 and hyperparameter 2, right? So with this way, with this technique, you are not having only few number of values for hyperparameter 2 and hyperparameter 1, but there are many number of hyperparameter values that we are using in this technique, right? For example, in the grid technique, we are using in this example 1, 2, 3, 4, 5 values, right? Hyperparameter 2, we have 1, 2, 3, 4, 5 values for hyperparameter 2, right? But with grid technique, you are using 1, 2, 3, because these three are actually slightly different values. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now there are 20 different points, right? For hyperparameter 1. So similarly, if you count the number of hyperparameter 2, there would be roughly 20 different values for hyperparameter 2. Right? So because we are selecting them randomly, we are having different values without restricting to a set of values in the uh, grid search technique. Right? So when there are many number of hyperparameters, practically this random search works better compared to grid search, because we can't have test for all the grid points when we are having a large number of hyperparameters. But this random selection can be used step by step, right? For example, you can use this technique with hyperparameter 1 and 2, and suppose you find that around this particular data point, this particular combination of hyperparameter 1 and 2, you have the best performance or the least amount of error. So you can add more data points around this data point, and do that means you can create random values around these data points, and then you can search around this data point, and then you can find exactly at which point you are having the best optimum combination of hyperparameter 1 and 2, and so on. And then you can zoom in again more and add more values, more random values in around that particular point, and then continue, right? So in this way you can step by step you can zoom into the points where the hyperparameters are getting optimized, and uh, hierarchically you can train the uh, train for the optimum hyperparameter values, right? So that is one technique that is an alternative for the grid search. Other than these two techniques, there are some other techniques as well. For example, Bayesian optimization, where you are using the Bayesian technique for instead of using the grid. Actually, it's a advanced, uh, much more advanced technique than grid, where in the grid view have to search in all the values, but with Bayesian techniques you can probabilistically estimate to which direction that you have to move your vector in the context of hyperparameters, and then you can go there and dynamically predict the values, right? So that means you can change the training uh, space around the hyperparameters in dynamic way using Bayesian optimization. So we are not going to uh, discuss about that, right? So which is a much advanced technique than grid search and random search, where it can dynamically search through the space uh, in the continuous way, right? So it is much faster and accurate one, but still it is not the optimum algorithm, but it's also a heuristic algorithm, right? And like the gradient descent technique that we have learned, there are gradient basic optimization for hyperparameter tuning as well, right? So when it comes to gradient descent algorithm, we are discussing about parameter searching, right? So in the machine learning, what we are doing is we are looking for the values for parameters. When it comes to the hyperparameter tuning also, you can use the gradient based techniques like the gradient descent algorithm, right? So as the as we discussed in the gradient descent algorithm, for these gradient based optimizations also need the requirement where the function is differentiable, or function should be continuous and differentiable in all the points to use this optimization technique, where, as we discussed there, you have to move your gradient. We have to uh, move from one point to another in a continuous space, right? So for that particular reason, you have to have a differentiable and continuous space in the uh, hyperparameter space, right? So if you can make that assumption, you can use the gradient based optimization. And there are some other techniques like evolutionary algorithms as well, right? So these eliminate these evolutionary algorithms are used for machine learning, used as machine learning algorithms as well. Although we haven't discussed in this subject, where you can use you can randomly have some uh, you can get, take the population of living beings as an example, and then you can evolve them in the in a technique similar to the natural selection that is there in the uh, animal world, where you can have uh, you can apply the mutation and crossover to for modifications in these populations, and then you can propagate the healthy or optimum features to the later generations by removing the unwanted or non-optimum data points, non-optimum values from the population, right? So in this technique also you can used for hyperparameter tuning, so that you can come to an optimum point with some extent, some level of accuracy, right? Okay, now let's discuss about the model evaluation, right? So we have discussed about data balancing techniques, and then discussed about the hyperparameters tuning, and now let's look at model evaluation. Uh, when it comes to the machine learning model development process, there are mainly two phases that you have to have, right? Uh, one is there are two things basically you have to do, right? The one is optimizing for model, right? Using uh, feature engineering or feature optimization, right? Which we have learned earlier, where you can like create new features, remove some features, or reduce the number of features using techniques, something like dimensional reduction techniques like principal component analysis, and do many things for feature selection, feature uh, engineering, and all those things for uh, dealing with the features, so that you can get a better machine learning model, right? And also in last couple of slides we have learned that we can tune the hyperparameters using hyperparameter tuning techniques, and we can have optimum hyperparameter values, right? So after this process, uh, we can after these processes of feature engineering or feature related optimizations and hyperparameter related optimization, we can have different machine learning models developed, so that we can evaluate these models, uh, and we can find the best model using the uh, using some evaluation criteria, right? So in order to evaluate the model, you should have some performance metric for evaluating the best machine learning model, right? So when you identify the best machine learning model, then you can identify what are the best feature engineering techniques, and what are the best hyperparameter uh, optimum hyperparameter values for each of the uh, for our scenario, right? So what we are doing in the model evaluation, as we discussed, we are evaluating against a new data that is not seen during the training process, which is known as the testing process, right? So we know when we are training a model, we dedicate a small partition or of data, small proportion of data, like 20% or 30% of data set for testing. Okay. So now let's listen carefully, right? We can change the features, right, using the feature engineering, as I explained earlier, and you can change the hyperparameters like that with hyperparameter tuning techniques, right? And then you can evaluate the model for each of these uh, feature engineering values and hyperparameter values against the test set, right? And then we can find the optimum model, right? So when we do this process, what happens is you would come up with many features, feature engineering optimizations, and many hyperparameter optimizations, and you will come up with many number of machine learning models which we are going to test with the test data set, right? So when we are testing with the this feature engineering techniques and the hyperparameter tuning techniques, in order to find the best model, you have to test these models again and again with the test set, right? You train with the training set, and then you have to test with the test set. So that sounds okay, right? That sounds okay because we have to train with the training set, and the test set is not used for training. We can use the test set for testing, right? But actually, there's a problem. There's a big problem, right? So the engineer or the user or the data scientist is selecting these different feature engineering techniques and hyperparameter optimization techniques for having the least amount of error, right? So when they test again and again with the test set, what he's actually doing is he is unknowingly optimizing to the test set, right? The user is actually changing the hyperparameters and do some feature engineering to reduce the error in the test set. In other words, he is trying to optimize for the test set. So when you are using test set multiple times and trying to optimize it, you will find some values for hyperparameters that are optimized for the test set, and the features, feature engineered techniques and reduced features or new features that are optimized for the uh, test set, right? So when we are testing with the same test set, that would be having some effect similar to the overfitting that we have discussed with the training set, which has also happened to the test set, right? So this is a big problem, right? So we are trying to keep the test set as a very independent and unblemished virgin data set for testing or evaluating the models. But now, because we are testing for many models and we are trying to reduce the error in the test set, we are making some differences, some changes in the hyperparameters and so on, and we are trying to reduce the error again and again to reduce the test set error. But here what we are subconsciously what we are doing is we are trying to optimize for the test set, not for the unknown data, but because we have a fixed data set for the test set, we are trying to optimize for the test set. So machine learning process is actually a process which is optimized for the training set, and this feature selection and hyperparameter tuning becomes a process which should optimize him for the test set. So although we find a set of hyperparameters and feature engineering operations that are very low in test set error, that may not be generic for the unseen data, because we have selected those values for optimizing for the test set. Right? So if we want to avoid this overfitting happens on the test set, we have to find another. So this is a bias, right? So this is a bias that is there in the test set. So in order to avoid that, we have to actually the only way to avoid this issue is using another data set for test set uh, for actual test in the data set for getting the numbers, but for model selection, that means when we have many models, in order to find the best model, you should not use the test set, but you should use the another data set known as the validation set for validating the for actually not validating, it's actual testing, but it is another form of test set which is used only for selecting the models, right? So in here, instead of two sets like training and testing, we have another set known as validation set, where we train with the training set, then we validate with the validation set. Actually, during the training process, it would be the data set would be this model would be optimized for the training data set for some extent, and then you have a set of models, and then you have to find the best model among the trained models, and then we are using the validation data set for finding the best model among the developed, among the trained uh, machine learning models, right? So during that process, these models would actually be get somewhat optimized for this validation set as well, right? So, however, when we are going to publish the results, that means when you are going to evaluate the exact values for the performance of these models, we should not be using this validation set, but we should use some unblemished uh, uh, data set known as the real test set, which should be kept apart from all these processes like training and selecting the model for testing, getting the values for that means getting the error values or the performance values for the machine learning models, right? So the idea is uh, that when we are using the training set for training the models, and for selecting the best model, we can use the validation set. But once we have selected the model, in order to get the exact performance numbers for this particular selected uh, model, we should use the test set only once, because test set is, we should not be uh, training again and validate again based on the numbers that we have observed from the test set, right? So once you, that means actually that is not practical in reality, but the idea is that you should use the test set as less as possible, right? That means you should use the test set uh, less as possible for the uh, purpose, because uh, if we use test set multiple times, that means uh, you would have a very the data set would also get optimized for the test set as well, right? So the test set would be kept away during the process, And once you have selected the model, the test set should be used only once or very rarely for getting the numbers from the selected model. Right? So definitely these numbers would be somewhat worse than the numbers that you have received from the validation dataset, right? Because the validation dataset is actually selected, is used for selecting the best model. So in while you are selecting the best model, your best model is actually optimized for the validation set. So in order to see what would be the effect, what would be the results of the with the uh, unseen data or the real world data, you should be using the test set which is not touched during the training or validation process, right? Okay, so that is what we mean by test set. So it should be used only once and can be used for evaluating, for representing the unseen data in the data set, right? The test set should not be used for the model tuning, because once we get the numbers, then you don't think that yeah, these numbers are not very good, so you should uh, find some other model or train with some other feature engineering or hyperparameter tuning. That is not a good thing, right? So that is not should be done habitually, right? So because at some time you would have to develop another model, but based on the test set values, you should not be uh, generating new models, right? Okay, here suppose now you have data in the data set with different qualities, right? For example, if you have high quality data and low quality data in your data set, for example, say your data set is a set of data points that are uh, taken from the exact population, right? For example, if you want to see the uh, students in a particular area, right? Uh, maybe you have some data that are taken from the students throughout the country. So that is higher in number, but for you would have some little amount of data taken from that particular area of the country, which is the most relevant data, right? So you should, when you have a data set like that for training the model, of course you can't throw away the uh, less important, the less quality data from the data set, because you want more data to train the model. So you should be using the country-wise data, countrywide data to train the model, but you should keep the highest quality data, which is the relevant area related data, as the test data, so that you can evaluate the model and find the exact performance numbers uh, that would be coming in the real world scenario, right? So the idea of using the test set is, as I always say, is to see how it behaves, what is the performance that you get in the real world application, right? Because of that, when you are using test set, or when you are selecting data for the test set, you should use the highest quality data, or the data that is highly representing the nature or the natural world should be used for testing data. Otherwise, you may have higher accuracy, but when you are deploying it in the real world, you would not have that accuracy, right? Because of that, when you use the closest, most realistic data should be used in the test set, right? So it is a very big challenge to uh, develop your model with the low quality data and get higher results when you have limited amount of high quality data which is not which are the most relevant data used for test set, because the highest quality data is not used for training but for testing, right? So that is the problem, right? So that's not a problem. So that is the challenge, because if you're using these highest quality data for training, then you won't have any data to test it, right? Maybe you can use, if you want to use this data for training, maybe you can use the techniques like cross validation and so on. So we will be discussing later, right? So in most cases, but the highest quality data, the idea is that the highest quality data should be used for testing, uh, and lower quality data should not be used for testing, because otherwise your entire research would be misled with wrong result or wrong performance numbers, right? When it comes to performance matrix, that means there are two types of performance matrices, right? One for so in this case we are discussing about supervised machine learning, right? In supervised machine learning, there are mainly two types of model: regression and classification models, right? In regression model, mean absolute error is one of the technique, right? For evaluating the uh, regression models, where you take the data point and the predicted value and take the absolute difference, and then we add these errors, absolute errors, for all the data points and divide by the number of data points, right? This is how we get the mean absolute error. So you know how to get the mean square error. So instead of using this absolute value, you can get the square, and then you get the mean square error, right? So square root of the mean square error is known as the uh, root mean square error, right? And also we have discussed about the coefficient of determination, which is also a regression model performance metric, right? Because we have learned about these techniques previously, we are going to today we are going to discuss more about the classification model related performance matrices, right? So those are accuracy, precision, recall, which is also known as sensitivity, and F scores, and ROC curves, and AUC, which is known as the area under curve, and the confusion matrix, right? So before we go into the uh, performance evaluation matrices in classification models, we have to uh, learn about some of the measures that are there in the classification models, right? When it comes to classification models, these measures has to be remembered, right? So because these measures are the measures that uh, are used for evaluating the classification model, right? The first one is known as true positive, right? So these four are actually true true, false false, positive negative, positive negative, right? That means this is a matrix between true false and positive negatives, right? So true positive means the samples where the model predicted the class correctly, and the actual class was also that class. That means so when the model has predicted the positive class, right? That means, so there can be several classes, right? When the class is the predicted class is a positive class, that means, so when the other classes are the negative classes, and it is true, then that is taken as true positive, right? Suppose not the positive class, but the negative class is predicted and it is true, it is known as true negative, right? And if the positive class is predicted but it is not true, that is known as false positive, or known as the type 1 error. If the negative class is predicted and it is not correct, it is false, that is known as the false negative, and also known as the type 2 error. Now, these four measures has to be remembered to further learn about the performance evaluation for classification model. Right? This confusion matrix can represent these measures. Yeah, the predicted class is positive and the actual class is also positive. That means it is a true positive value. When the predicted class is positive and the actual class is negative, it is a false positive, because it's positive, but it is not the positive, but it's negative. Because of that, it is false, right? The predicted class is negative. That means it's a negative outcome, but the real outcome is positive. Because of that, it is a false one. It is a false negative, right? If the predicted class is negative, right, but the actual outcome, actual class is also negative, then it is true. Because of that, this is known as the true negative, right? This is how the confusion matrix can be built, right? So now let's move to the accuracy, move to the performance measures of classification model, right? The most widely used and most clear performance matrix for classification models is known as accuracy, right? Accuracy is the most simple and very clear performance measure, which is the proportion of correctly classified instances, right? Number of correct predictions divided by the total number of predictions made. Very easy to understand, right? Which should be a value between 0 and 1, right? So accuracy would be a value between 0. That because 0 means no accuracy. Accuracy 1 means 100% accurate, right? Whatever number of correct predictions divided by the total number of predictions. For example, in a binary classification problem, predicting 90 samples correctly out of 100 samples, that means suppose there are 100 data points, and if the model can predict 90 data points accurately, then the accuracy is 0.9, right? But there's a problem. Although this is a very clear and very intuitive performance metric, there's a catch, right? So this accuracy only works when the data balance is there, right? That means when the proportion of data in all the classes are equal, then we can consider accuracy as a very good performance metric, right? But unfortunately, because in the real world data are not that class balanced in classes, because there are some imbalance or in other words, there are some imbalance in classes, accuracy would not be a very good predictor, right? So let's see why it happens. So in the earlier case, we said that if there are 100 samples and if we can predict 90 samples correctly, we can get the accuracy of 0.9, right? But suppose that all the 90 data points are positive samples, right? And the error 10 data points are relevant to negative data samples, right? So still it would be accurate. The accuracy would be 90% or 0.9, right? Accuracy would be 0.9. But in reality, the model has not predicted any of the negative samples, right? It has predicted all the positive samples, all the 90 positive samples, and all the negative samples also as the positive samples, right? So, so a model which returns positive in all the times, predicting positive for all the predictions, can be 90% accurate. The accuracy can be 0.9. So when someone doesn't know about this phenomena, would say that my model is 90% accurate. So they would say, wow, it's very fantastic, right? So it's 90% accuracy for a machine learning model is significantly better, right? But none of the negative examples were classified correctly. What has happened is that this model has optimized for these 90 samples because the 90 is it's a very high proportion compared to the 10 negative data points. The model might have learned to give positive for all the outputs so that it would give positive as all the outputs for including these 90 positive samples and also for the 10 negative samples. But although it is 90% accurate, this is not what we want. Right? We want to classify these negative samples correctly, especially when it is especially when we want to classify these 10 data points, because suppose something like diagnosing the HIV patients, this 90% of this 10% or 1%, the samples is very important, right? To be predicted accurately. If we predict them as not infected, that would be a very big problem, right? Because of that, accuracy would not be a very good performance metric when it comes to highly classed, imbalanced data samples, right? So what can we use? There are several options, right? Say, so precision is one of them, right? So what is precision? Precision is the accuracy of positive predictions of the model, right? So we take the true positive predictions divided by the total number of positive predictions done by the model. Right? True positive predictions means the true positives. Total number of positive predictions is the true positives plus false positives. So if you are not sure, you can just think slowly and calculate these values. So you will find this is the equation, right? Precision is also a value between 0 and 1. So the idea of using precision as the performance matrix is to reduce the false positives, right? So suppose a scenario like this, right? A court or the judiciary is going to give a death sentence for a person, right? For murdering charges, right? So he would be given death penalty for this particular charge, right? So in that kind of scenario, the court is highly concerned for not giving the death penalty to an innocent person, right? When the court is given to give the death penalty to a person, the court is highly concerned not to give the death penalty to an innocent person, right? So because of that attempt, because of that priority, a true murderer may escape from getting the death penalty, right? That is the nature, right? So even with that kind of possibility, the court doesn't want to make chances of giving the death penalty to an innocent person, right? So the idea is to reduce the false positives. So that means giving false positives means giving false punishments, detecting positive as a murderer. Suppose that is the positive, So we want to reduce these false positives as much as possible, right? Even sacrificing the real murderers not getting detected, right? So that is what we have to pay, but the importance is not to punish an innocent person, right? Especially the death penalty, right? So in that case, that kind of situations, you can use precision, where you are trying to uh, avoid the false positive. But during this process, uh, the amount of information, that means the correct information that you can retrieve from the data set would get sacrificed, right? That means, for example, when the court is trying hard to uh, being strict with the evidence that are against that particular person, that means if they are not that certain uh, that this person has committed this crime, the court would not give him the death penalty, right? With that, with this probability, the real, that particular may be a real murderer and he may get escaped with a higher probability, but the highest danger is innocent person getting punished with death penalty uh, while trying to uh, identify a murderer, right? So in this kind of requirement, the precision can be used. The opposite of the precision is known as recall, where you want to you don't want to uh, optimize for the accuracy of the positive outcome, but we want to get outcomes as much as possible. In other words, we want the test to be highly sensitive, right? For example, when we are uh, trying to identify a terrorist suspect during the uh, flight, during a flight, right? You should not take any risks, right? For example, if there's any, if you think a certain passenger would be having some explosives in their hand luggage, you should not let him go into the plane, because otherwise, with this probability, there would be a catastrophe in the future, right? You should not allow that kind of scenario. So you should always try to search him as much as possible, although in most of the cases he would be an innocent person, right? So when it comes to selecting people for searching for being a terrorist, when it comes to the passenger boarding into an airplane, we should use a model which is very sensitive, or which has a higher recall, right? So that is the opposite of the precision, right? So here what we are trying to do is the recall is the true positive predictions divided by the total number of actual positives, right? That means for the given set of positive outcomes, how much of true positives are given. That means we want to maximize the true positives uh, given, although there can be uh, false positives as well, right? So the idea is to reduce the false negatives. So being a terrorist and not getting detected is the most dangerous situation, right? So you should avoid it in all the costs, right? So when it comes to the true positive predictions, it's denoted by the true positives. The total number of actual positives can be represented by the total positives plus false negatives, right? The recall would also be a number between 0 and 1, right? So this is how, that is the difference between the precision and the recall. But as I discussed in the precision, when you are using recall, there would be a high probability that an innocent person would be suspected as a terrorist and he would be searched or he would be bothered in the airport. But the idea is to reduce a real terrorist blowing in the airplane. So we have to use recall as the uh, performance measure when it comes to detecting possible terrorist in the passengers, right? Among the passengers. So as we discussed up to now, we know now accuracy cannot be used when accuracy would not be that much accurate when the classes are imbalanced. And we said that there are opposite types of performance measures that we can take, precision and recall, right? Suppose we want to have both precision and recall, right? In some scenarios, we should have both precision and recall in certain proportions, right? For example, some may want to have uh, equal weight for precision and recall, right? So when you increase the precision, you would reduce the recall, and when you increase the recall, the precision would be decreased. But if you want a balance in between them, it is half of the precision and half of the recall. Uh, you can use the average of this, right? You can take the average of precision and recall and make a measure, right? That is actually how we make the F measures. But however, mathematically, when taking the average between precision and recall, you can't take the common average like this, like precision plus recall divided by 2. This cannot be used, right? So we are not explaining why this is not possible. This is related to mathematics, right? So there's a mathematical explanation, but what we have to use is not this common average, but the harmonic mean. The harmonic means it is not just precision plus recall divided by them 2. It, in this average, it is the average is calculated by precision times recall times 2 divided by precision plus recall, right? This is how the high harmonic mean is calculated. So actually you can search more why we are using harmonic means for precision recall, but for the moment just remember this is how we calculate the average between precision and recall uh, when it comes to calculating the F1 score, right? So F measures, there are different F measures. F1 is one of the F measures, also represented like this, right? F1 measure is taking the average or the harmonic mean between precision and recall, right? So this is the formula for calculating the F1 score. But F1 is not the only measure, right? Sometimes we want to have different proportions in precision and recall, right? For example, we want higher amount of precision and low amount of recall, or higher amount of recall or low amount of precision, right? You can tune this value using this F beta score, right? In the when you calculate in the uh, F measure, right? So this F beta score can be calculated like this, right? So like instead of F1, we can have F beta where you can have this tuning parameter, in which proportion you want. So not the exact proportion, but a certain value related to the proportion. You can calculate this F beta score using this formula where F beta score is also lies in between 0 and 1, right? So it is like 1 plus beta square divided by b precision times recall divided by beta square times precision plus recall. Right? With this formula, you can calculate the f beta score, which is where when the beta is 0, you can get the precision or the f0 score. When beta is 1, you can get the f1 score, which is 2 times precision times recall divided by precision plus recall. Right? And when beta is greater than 1, you can get higher weight for the recall and lower weight for the precision. Right? For example, when it comes to f2, it is 5 times precision times recall divided by 4 times precision plus recall. Right? When the beta is lesser than 1, precision increase and the recall decreases. Right? For example, if 0.5 measure, you can get 1.25 times precision times recall divided by 0.2 times precision plus recall. Right? So there are some examples for F measures. So we discussed that the precision measures the accuracy of positive cases. Right? Similarly, the specificity is another measure which measures the accuracy of negative cases. Right? Precision is a measure for positive cases, accuracy of positive cases, and the specificity is a measure of accuracy of negative cases. So here we can see the specificity is defined as the true negative predictions divided by total number of negative predictions. Right? True negatives divided by true negatives plus true false positives. The specificity also lies in between 0 and 1. Right? Like precision, we discussed that when we have higher precision, uh, it leads to higher false positives. Right? Similarly, when you have a higher specificity, then there would be higher false negatives as well. Right? So sometimes this may not be intuitive that much, but the reality is that when it comes to specificity and sensitivity or the recall, there's an inverse kind of relationship. Right? Because of that, you can make a graph between specificity and sensitivity, or the specificity and recall, using ROC curves or receiver opter characteristic. Right? The one-axis is the true positive rate or TPR, the sensitivity calculated by this formula, which is TP divided by TP plus Fn. False positive rate, which is 1 minus specificity, or false positive divided by Fp plus Tn, right? False positive plus true negatives. And we can see what are the trade-offs between specificity and sensitivity. Right? So these ROC curves are generally used in medical applications where we want to balance how much sensitivity and specificity should be adjusted depending on the scenario, right? So depending on the risk and risk of several two different uh, trade-offs, right? In medical field, you may be using these ROC curves, right? Receiver opter characteristic. So we will see in the next slide how they are used, right? So it is like this, like in the x-axis we can take the 1 minus specificity, or and the y-axis you can take the sensitivity, right? So when there is no relationship in the model, that means when the model is randomly predicting, it would be given as this orange color line, right? If it is accurate, it would be give a model something like this, right? Like the blue curve. If it is 100% accurate, it would be a line like this. So the accuracy, so the value, the area under this curve, so there can be different curves you can draw depending on your machine learning model. So the area under this curve is a measure of the accuracy, right? So AUC is the measure known as the area under the curve, and that is a measure of performance in this binary classifier, right? For pure classifier, that means for 100% accurate classifiers, the area under the curve would be 1, right? So because 1 times 1 times 1 would be 1, right? So the area would be 1. For random classifiers, it would be 0.5 because this triangle area would be 0.5. Right? So something in between would be a significant classifier, right? So which would be giving some accurate values, not 100%, but in between 100% and random values, right? It would not be random, but it would be somewhat accurate, right? For example, this blue curve is a example. It's an example for a real world ROC curve, right? Okay, so now we have discussed about the performance evaluation matrix, right? Up to now, we haven't discussed about the uh, cross validation up to now. Right? So now let's see what is cross validation. So we discussed that when we can use training sets and test sets, depending you can have a smaller value for test set and large value for the training set. And also we have discussed that when you are selecting models, using the test set for selecting the model is not good because then the model would get optimized for that particular test set. So you should use a validation test, right? Validation set, right? However, these things are only possible when the data set is sufficiently large, right? That means if the data set is not sufficiently large, then your training data, when you are dividing your training data, dividing your data set into two at least to two sets like training and test sets, the test set would be very small, and because you have dedicated some data points for the test set, you would have a lesser amount of data to be trained, which is another problem, right? So because you have lesser amount of data to be trained, your model would be less accurate. So that for the testing also, you are using a very little amount of data for testing. You would not have a very correct measure of the test of the accuracy in your data set, right? Because the test set is also small. So what can you do is, if you can use all the data points for testing and all the data points for training, maybe you can get a better value for uh, test error, right? So what I mean is that if you can, instead of using a very small proportion of data for testing, if you can uh, use all the data points for testing and get the average, then you would have a better value, right? Instead of using uh, a single small data set for testing, you can use several uh, data sets for testing and the remaining data sets for training, right? And then you can get the average, then you would have a better testing error, right? So that is the idea of cross validation, right? In cross validation, we are reusing the same data for both training and testing, right? And then we can get the average for test errors, and then we can get a better test error, right? So we can use this technique for when you have lesser amount of data for training and testing, right? Say we have a data set, a small data set, and then we want to divide it into 5 partitions, right? Where we are going to say, like, we are going to test with 20% of data, and we are using 80% of data for training, right? So what we do here is, so this is the example. Say this is the whole data set. We are so we are using this data set in 5 iterations. In the first iteration, what we do is, uh, in all the iterations, actually we divide this whole data set into 5 partitions, equal partitions. We use the first 4 partitions for training and the last partition for testing, right? The first iteration. This blue color is the training data set, and this white color is for testing data set. This gray color, right? Yeah. And then we get the error. So let's take this as error 1. For the second iteration, we take the third partition for testing and the remaining partitions for training, right? From here you can get the error 2, right? For the third iteration, we get the third partition for testing and the remaining partitions for training, right? From here you can get the error 3. Similarly, you can use the second partition for testing and the remaining partitions for training in the iteration 4 and get the error 4. For the last iteration, you get the first partition for testing and the remaining partition for training, and you get the error 5. So now we get all the errors for all the iterations, the 5 errors for all the iterations, and then we sum all these errors from 1 to 5 and divide by 5. Then we get the average error, right? So this error can be used as the error of the model. So if you were using just training and test set, you would be actually using something similar to the iteration 1, right? So you are only taking these first 4 data partitions for training and the last partition for testing. But with cross validation, we have used all the data points for testing. So by taking the averages of the errors, we would have a better error, so that you can use it much more reliably, right? So the advantage is that you can have better error. You can better uh, performance measure. The downside is that you would have to train it multiple times, right? Suppose now you have a very less number of uh, data points. You can further extend this uh, techniques for not only for 5 partitions, but for n partitions where there are n data points. You can extend this, instead of using 5, you can use the number as n, right? So when you are using the k as 5, or you divide it into 5 partitions, this is known as the k-fold cross validation, right? We have taken 5 as k as 5, right? And when we can take k as 1, that means for at each iteration we are taking only a single data point for testing and using all the other data points for training, and you have to do the iterations up to the number of data points. So if there are n data points, you have to have n iterations and get the averages of the errors. So this is known as the leave one out cross validation. So this is a special case of this k-fold cross validation, where we divide the data set into k times. For example, 5 data partitions, but with this cross validation, with the leave one out cross validation, you have to divide the data set into n data points, and then you have to then you can apply the cross validation. Right? This is the most extreme type of cross validation, where you have to train the with the machine learning model for all the data points, right? Using them as test values. This can be used when the given data set is very small. Right? Okay, so now this is all for the today's lesson. Right? If you have any questions, you can ask.